Good afternoon, everyone. For those of you who don't know me, I'm Chris Johnson, and I'm the new Pro Vice Chancellor for Engineering and Physical Sciences here at Queen's. It's an enormous pleasure to welcome you to this afternoon's talk on behalf of the Royal Irish Academy and the Chief Executives Club and the School of Mathematics and Physics here at Queen's. I'd also like to extend a very warm welcome to Professor Vlatko Vedral, who's one of the top scientists working in quantum physics. As with many of these events, it's a real disappointment that we couldn't all meet in person. And obviously, because we've had to move to the online platform, there are certain courtesies that I would hope everyone would follow. So I would appreciate it if people make sure that they remain muted and their cameras off during the presentation. However, if anybody would like to pose any questions at any particular point in time, please feel free during the talk or any time to use the chat facility. Provide your name and organization, and then my colleague Mauro Paternostro, who's the head of physics and mathematics, will pose the questions towards the end of the presentation. Once the presentation concludes and also the question and answer, then Professor Jerry McKenna, Vice President of the Royal Irish Academy, will make some closing remarks. I'm going to pause now and confess that I am probably the least qualified person to introduce the topic of the John Stuart Bell Day and also the speaker, because I come from a background in human spaceflight and mission assurance, where understanding the reliability of computational infrastructures is absolutely paramount. And I really struggled over many years to understand the basics of quantum physics. So it's a sense of trepidation that I introduce a talk on this topic with so many great connections to Queen's. And I'm responsible for, I think, one of the most ignorant statements that will alienate every single person in this audience. But hopefully I'll win you back by confessing that it was an ignorant statement and tell you how the joke is on me. So I was asked to do a funding review of quantum in computation. And I said, while this area has great potential, there is the small possibility that it ends like nuclear fusion with the same inputs and the same outputs. So at that point, I realized I've alienated every single person on this call. But the joke ended up on me because I've, in the last 12 months, been involved in the launch of quantum key distribution satellite, doing the mission assurance on that. And I've had to really learn a little bit about the fundamentals of quantum, just the basics. And as I said, I struggled because I'm familiar with the conventional computational model. But a friend of mine at MIT sent me a joke that gave me the first inkling as to how all this thing stacks up in terms of the computational side. So the joke goes, time flies like an arrow and fruit flies like a banana. And in order to understand the humor in that joke, you have to hold both concepts in your mind at the same time. So I tried to explain this to my kids, and one of whom works in quantum, and he looked with a sense of sorrow, not that I'd been able to understand quantum, but that I could find any humor in that statement. So you understand that I am both embarrassed and probably unqualified to introduce today's topic. The lecture series is obviously named in honor of one of Queen's graduates, John Stuart Bell. The series began in November 2014, and it's hosted jointly, as I said, between the Royal Irish Academy and the Chief Executives Club at Queen's. The aim is to raise awareness of the contribution of this remarkable scientist, whose discovery in November 1964 changed the whole of science by laying the foundation stones for quantum computing through his quantum theory. The Royal Irish Academy, founded in 1785, is the Academy for the Sciences and Humanities for the whole of Ireland. The Academy continues to play a pivotal role in Irish society and brings together academia, government and industry to address issues of mutual interest and intersection. Chief Executives Club is important in forging connections between the university and the business community, and information about all of the hosts and the background can be found online via, for example, the Queen's website. I also want to say welcome to Dorothy Whiteside, who is John Bell's niece. It's particularly an honor for us to have you join us and to correct me for any factual mistakes that I've made at any point during either my introduction or the welcome. In a nutshell, John Bell is known for his work that produced Bell's theorem, and that's the benchmark for quantum mechanics and for experimental physics. And as I say again, I feel underqualified both to even to do the introduction or to provide any forward to this talk. He was nominated for a Nobel Prize and described by the Institute of Physics as one of the top 10 physicists of the 20th century. Bell's theorem was first published 56 years ago on the 4th of November 1964, and that's why today is chosen to celebrate and mark John Bell's Day. He was born in 1928 in Belfast in a working class background and attended Belfast Tech before working as a junior lab assistant in the physics department at Queen's under Carl Emilius and Robert Sloan. They encouraged his ability. He achieved 2 first-class honours degrees at Queen's and went to complete a PhD in England before working at CERN. I'd like today in this lecture to just pay tribute to a truly great scientist, and now move on to say a short introduction to today's speaker. Vlatko Vedral is Professor of Quantum Information at Oxford University and also Professor of Physics at the National University of Singapore. He joins us today from Oxford, and Vlatko, you're really welcome, even if it's only virtually, to Queen's University Belfast. And I know that everyone involved here in Queen's would really welcome you physically as soon as time and circumstance allow. Vlatko studied for his own degrees at Imperial College and has published over 350 research papers on topics relating to quantum physics and quantum computing. He's in the Clarivate list of highly cited researchers, which means he's one of the most referenced research workers across the world. He's given many conferences and public talks during his career and was awarded the Royal Society Wolfson Research Merit Award in 2007, the World Scientific Medal and Prize in 2009, and the Marco Jurasic Award in 2010. Fellow of the Institute of Physics in 2017, and a member of the European Academy of Sciences in 2020. And at this point, I feel like I've imposed on you beyond measure. I'm delighted that Vlatko can give the 2020 John Bell Day lecture. Vlatko.
Thank you very much, Chris. I hope that everyone can see me. It's a real pleasure to be talking to you today. I will share my slides, and I hope that nothing will go wrong at this point. Here we go. Is everyone able to see the slides? I hope you are. And today's lecture is really very much influenced, as we've heard, by John Bell's thinking. And you will see as we go along that I will borrow many ideas and many phrases from many other great physicists, actually, that certainly John Bell belongs to this crowd. It's about quantum reality. And of course, already the language there that I'll be using is exactly what Bell has been thinking about and what bothered him actually when he was thinking about the foundations of quantum mechanics. He somehow turned all of these philosophical ideas into something practical, as we heard. And in fact, we even use it now, as Chris mentioned, for benchmarking our experiments and quantum cryptography and so on. Now, my first slide, as always, introduces quantum mechanics. And these are phrases that most of you will recognize from another great physicist, of course, Albert Einstein, who complained a lot about quantum mechanics. And it's quite interesting, in fact, and quite ironic in many ways, that these two complaints of Einstein have in fact become really the foundations of quantum mechanics. So his first complaint is that God doesn't play dice. He didn't like the random element element in quantum mechanics, which I will illustrate with a very simple experiment. And the other thing he didn't really like is the thing he calls spooky action at the distance. Of course, this is all to do with Bell's work and superpositions, entanglement, and Bell's inequalities ultimately. So what Einstein didn't like about quantum mechanics is that even the most basic quantum experiment, which is the one on this figure, where you send a single photon in from this side at a beam splitter, which is a piece of glass that acts like your sunglasses. So it has a certain probability to reflect the photon, and it has a certain probability to transmit the photon. What happens in any actual experiment is that actually which of the two detectors will click is a completely indeterminate or even unknown or random, whichever language you want to use. It's something that the theory really cannot give you. And it's a breakaway from the classical determinism, where if you know exactly what you're doing, if you know all the initial conditions, you'll be able to predict everything. So here, every time you fire a photon, it randomly ends up in detector 1 or detector 2. And it's only when you repeat this many, many times that you might get the statistics to build up. And that's, of course, something that quantum mechanics then ultimately predicts. So if it's a 50-50 beam splitter, half of the times detector 1 will click, half of the times detector 2, but we won't know which one. And that's the aspect that actually has been confirmed. The beauty of this is that even if you think it's unusual as far as classical physics is concerned, then every quantum experiment is uncertain to exactly the same degree as the one with a photon. I could have used an atom, I could have used a complex molecule, I could have used a large aggregate of atoms. All of them behave exactly the same way. Now, coming back to the second complaint of Einstein's, is that if you don't detect this photon, but if you let it reflect of two mirrors, and then you put another beam splitter there, the interesting thing is that now you recover complete determinism back. And that's very interesting, because every time you fire a photon here, you get only detector 1 to click and never detector 2. And the question is, how is this possible? How can you take a random thing, a beam splitter, and put another random thing and recover perfect determinism? And you know, people like physicists like Richard Feynman would have said, this is the only mystery really in quantum mechanics. How can it be like that? And our explanation to this, which is of course why Einstein was complaining about it, is that in fact, if you ask which path does the photon take after the first beam splitter, the answer really ends up being both at the same time. So the photon exists in one arm, this is a single photon, in one arm of the interferometer and the other one simultaneously. And when these two arms meet at the second beam splitter, they somehow amplify each other, much as waves would. They're in phase, if you like, when they go in this direction, and they completely cancel one another out when they go into the detector 2. And this is this famous notion of a superposition. So the photon really exists in both of these arms simultaneously. For otherwise, this experiment could really not be explained if you assume that the photon goes one way or the other, but not both of these ways. So somehow Einstein felt that this is very spooky. He didn't really have a quantitative way. That's exactly what Bell did. He didn't have a quantitative way of saying how spooky this is, but he felt that something being in two different places at the same time is actually somehow weird. That should not be allowed. It's kind of non-local. And of course, he disliked this because of his theory of relativity. And then, of course, came Schrödinger, and another great thinker, who said, well, if you think that the microscopic world is weird, and if you think that photons and atoms behave in this way, that they can exist in many different places, in many different states at the same time, then the troubling thing really is that everything must be like that as well. Anything that couples to this microscopic system must also actually join in this weird superposed state. And that's the famous, by now, Schrödinger's cat experiment. Actually, he wrote He wrote 2 papers there, one in English, one in German. I think he was bilingual, and he coined the word entanglement in the English one. And basically all he was saying, it doesn't really matter. I'm using the symbols that we typically use in quantum mechanics, and you will see at the end why this is interesting as well. But all he was saying is that if you have 2 entangled systems, then the state of these 2 systems is very different to having a state of one of the systems and independently the state of the other one. Somehow you are forced to describe them jointly. They are more like twin systems rather than independent individual systems. And this is really an important idea. Here is basically a snow cat that my students, I think, made once when I sent them to a winter school, I think somewhere in La Zouche, I believe this was, and you can see a dead cat there and an alive cat. And how is this done now? What did Schrödinger actually tell us? I'm saying in principle with a smiley face there, because of course this is a stupendously difficult thing to do in the laboratory, and we are very, very far away from doing it. But of course, it's always good in theory and in our conceptual ideas to think about these experiments, which is exactly what Schrödinger was doing. So he would stick this cat inside this kind of interferometer that I was showing you with the photon. And then what Schrödinger said is, imagine the photon goes one way, and imagine that in this path, I put in a bottle with poison, which when the photon hits, the bottle is broken and the poison is released. And if I have a cat inside the same room with the rest of the experiment, then when the poison is released, the cat will be dead. But in the other arm of this interferometer, there is no poison. The photon happily goes along, doesn't break anything, and the cat simply stays alive. So Schrödinger said, look, if you think a photon can be in 2 different places at the same time, then I can easily take this micro tiny effect and amplify it to an arbitrarily macroscopic scale. And that's the problem with that, because now in one arm, the photon breaks this bottle, releases the poison, and the cat is dead. And in the other arm, the cat is alive because nothing has happened. And quantum mechanics actually suggests to us that this exists simultaneously, simply because the initial photon, as we acknowledged already, must exist in both of these arms in order to explain our observations. And as soon as this photon couples to the bottle with poison, to the cat, to the rest of the universe, somehow everything becomes split in exactly the same way. And that really is weird. And of course, it doesn't stop there. And this is something that I would like to explore for the rest of this talk, really, because now you can say, what if there is an experimental physicist who is actually looking at the screen of his computer and thinking, what happened inside this box? Is the cat alive or dead? He would actually also have to join in. He would become entangled, if you like, with the whole state. And in one branch of this state, the physicist would be very happy because the cat is alive, and in the other branch, the physicist would be probably devastated, if you like, and would be very sad that the cat is no longer alive. And that's it. Somehow, this tiny quantum uncertainty, if you like, the tiny superposition of a single quantum particle, in this case a photon, but you could do it with an atom, with a molecule, with anything. Suddenly, when that couples to other objects, they all become infected, if you like, with this quantum uncertainty and the superposition. And this is mind-blowing. And of course, this is the basis of our quantum technologies. That's precisely what quantum computers are trying to do, really, and to make these huge entangled states of many, many particles. Now, of course, Bell's contribution. And what did Bell say? Bell said, look, this is interesting. What is this telling us about the world? So he was really the first person to quantify this spookiness, if you like. And he gave us a simple choice there. I'm writing here again that the symbols really don't matter much, but I think what Bell had in mind is simply two electrons, two particles that could be spinning, and these arrows simply are telling us that when one electron is spinning one way, the other electron is spinning the other way, and vice versa. And when I say and, I mean it in this quantum mechanical way. They really are in these two states simultaneously. It's not either one or the other, it really is and. And so what Bell said to us is Bell said, look, we have two things that we like intuitively about the universe. One is this reality, that things exist independently of us engaging with the universe. Somehow there is a degree of independence that's really proceeding along without us having to engage in any shape or form. So that would be, loosely speaking, reality. Locality is the fact that if we do something in one location in the universe, we do not change anything else in the universe. And this locality principle is extremely important in relativity. That's exactly what Einstein didn't want to give up, and why he kept saying spooky action at the distance. I don't like quantum mechanics because of spooky action at the distance. And yet this spooky action is there. It's confirmed experimentally. Bell's inequalities have been violated many, many times. And so we know that we are facing the choice that Bell told us. So Bell said, either you have to give up the fact that numbers exist out there describing various properties without you having to really measure them. So if a car is moving at 30 miles an hour, then that statement is true, independently of whether you choose to measure this speed or not. That's kind of reality. What this 30 miles an hour really exists out there somewhere in the universe. And Bell said, either you have to give up that, or you have to give up the notion of locality, and you have to really admit that something can happen faster than the speed of light. In fact, entanglement would suggest that it can happen instantaneously. And it's a very stark choice. So using locality and reality meaning everything is made up of these real numbers, if you like, then basically you will set up a set of inequalities. And of course, as we know now experimentally, they happen to be violated. And loosely speaking, I'm saying here that this instantaneous action is there because whichever way you happen to measure one of these electrons, is it spinning upwards, downwards, left or right, the other spin, no matter how far away it is, will automatically adjust to spin in exactly the opposite way. And again, this is a behavior that you never see with classical spinning objects. There's no way that you can reproduce this kind of correlation. It's exactly what Schrödinger called entanglement. So somehow, when we are giving these things up, and I want to tell you what I would prefer to give up. I think Bell, of course, wrote many papers on exploring what it would mean to give up either of these things. He was even entertaining ideas that relativity may be wrong at some point. He certainly was entertaining the idea that maybe reality is of a different kind. Clearly, all of the other things that Einstein complained about still have to be acknowledged. They simply are true in quantum mechanics. And as I say at the bottom of this slide, I say this definitely signals to us that randomness is there, and this is a clear breakaway from what you would call classical causality. But I think the way we think about it in our modern times, and maybe in our field, is that rather than giving up this locality, because we know that we can never send messages faster than the speed of light. No experiment has ever been done to actually violate locality. What this signals to people like me, and I think many people would agree with this, is that actually reality is not what classical physics used to suggest to us. it's not made up of numbers. It's not that numbers exist out there to describe it, but what exists are what I called Q numbers, quantum numbers. They are more complex objects. They are operators. They're matrices, if you like. That's what Heisenberg introduced, and that was his first paper on quantum mechanics. So basically what I'm suggesting is that we should give up this notion of reality according to classical physics. And now I want to have two other catchphrases which describe this. And actually one of them comes directly from Bell's inequalities. I call this observing the observer. I already introduced the experiment of Schrodinger's cat, but now I'm going to introduce two experimental physicists, Alice and Bob, that are somehow going to get connected with this experiment. And that's where it gets interesting. So the first statement there that I have is unobserved results can affect future measurements. So what this signals to us is that even if you made an observation in your experiment, but you saw one outcome and not the other outcome, that other outcome that you didn't see in your experiment could still affect your measurements in the future. And I think this is quite remarkable, in fact. And that's exactly what entanglement, what this concept of entanglement implies to us. So one statement from Bell is that if you didn't perform experiments, you will never get classical reality out. You will never get real numbers out, and you have to live with quantum numbers. These are numbers that are really more complex. They don't have definitive values. That's the only reality. However, when you engage with an observation, you actually are in a different situation now. You can see an outcome, but actually the outcome you didn't see in the other branch can also affect your future, and that's quite mind-blowing, actually. And to tell you about it, I have this very simple experiment, which is an extension of Schrodinger's idea, really. So here we have the photon, and in one branch of this, the cat dies, as we said, and the other one is alive. And here we have another experimental physicist, Bob, who actually is in one branch of this reality happy because the cat is alive, and in the other one, he's very sad and he's saying bye to his cat. And here is another experimentalist who actually sits outside of the whole thing, and Alice, in this case, controls this whole experiment. So what can Alice do? And I think this is where it gets very, very interesting. What Alice can do is she can, first of all, confirm whether at the point when the cat is alive and dead in two different branches, whether Bob really sees either a living cat or a dead cat. So Alice can simply ask Bob, do you see either a living cat or a dead cat? And actually quantum mechanics would simply tell us that Bob would say yes, because in both of these cases, Bob sees a live or dead cat. Notice that Alice should not ask what outcome Bob sees, because if Alice asks that, then she joins in this entangled state, and there is a huge problem there, because then she cannot complete the experiment. So after confirming that Bob sees a definitive state, he's actually made a measurement, if you like. What she does is she reverses the whole thing. She recombines these two photons. She has to undo the coupling that results in the poison being released. This is extremely challenging. Like I said, no one can really do that, but this is what quantum mechanics suggests could in principle be done. And at the end of the experiment, she literally reverses the whole thing. That's actually the crux of the experiment, and this is the crux of every quantum experiment. You first make the superposition, and then you undo it and see whether the system will come out the same way that it came into the experiment. And if it does, that's what we call interference. That confirms that the system was really taking both of these routes simultaneously. So of course, here this would be very difficult, because you would have to undo the interaction with the cat, undo the interaction with Bob, and all of that. At the end of the experiment, Bob would come out and wouldn't even remember that there was an experiment because the whole observation would have to be undone. But the interesting thing is that if the photon came out exactly into one of the detectors and not randomly into both, so this could be repeated many times, this would signal to Alice that halfway through the experiment, even though Bob claims to have seen a definitive outcome, actually there were two Bobs, there were two realities, and both existed at the same time. And this is mind-blowing, but this is quantum mechanics. This is the kind of quantum reality. So as this slide says, halfway through, Alice has confirmed that Bob is really entangled to this cat that I call Felix here, who is then entangled to the poison, and the whole state is a huge entangled state. And interestingly enough, to bring it back to John Bell again, the way that Alice could confirm this would be very akin to how we do Bell's inequalities and how we confirm any entangled state. So mathematically speaking, at least, this is perfectly easy to write down and to calculate, but of course, it's extremely challenging physically to do this experiment. Now, here is an extra twist. Like I said, there are two bits to this. The twist is that each of the Bobs in this superposition of two alternatives could even know that the other Bob exists that sees a different outcome. And this is precisely why I'm saying even unobserved results can affect you in the future if you believe, of course, that the universe is quantum mechanical in the way that I'm describing it here. So Alice could even halfway through the experiment say, I know, Bob, that you told me that you see one and only one outcome. You either see a dead cat or a live cat, but I can reassure you that I've made measurements and I know that you exist in both of these realities. There is a copy of you, one of which sees a living cat and one of which sees a dead cat. And so this is really the most mind-blowing consequence of quantum mechanics. And it really complies with everything that we understand experimentally. And of course, now I'm using this Alice in Wonderland analogy where I'm saying, look, why stop there? There could be yet another experimentalist, in this case, Mad Hatter. You can see that it's very appropriate because we are getting crazier and crazier with these superposed realities and entanglements. There could be even another experimentalist outside of the whole room that now talks to Alice. And Alice keeps informing Mad Hatter about what's going on inside Bob's experiment with the cat and poison and the photon and so on. So all of these things within quantum mechanics become a huge entangled web of interactions. And basically the analogy that I have and that I'm very fond of comes from Wigner, another great physicist who thought very deeply about this. And we call it Wigner's friend. So Wigner's friend is simply a person that you communicate your experiments with. And because you communicate to this person, they invariably have to become infected by exactly the same quantumness that you are infected with. And so this is a little bit akin to this painter that tries to capture reality by painting everything he sees, in this case woods, around him to the exact minute detail. And when the painter finishes the painting, he realizes to his horror that actually it's still not complete and faithful because he himself, the painter, is missing in the painting. And then he adds this painter to the painting. But again, he figures out that now the painter painting the painter as well and the woods is still missing. And no matter how many painters you really include in this painting, you're never gonna capture the full reality. There is, of course, an infinite regression there. And it looks as though this could be a problem. And I think sometimes people complain about it, that nothing is ever definitive in quantum mechanics. And that actually is the punchline. If the world functions this way, no outcome, no measurement is ever definitive. And even things that you don't measure, like I said, could actually affect your future, providing, obviously, that there is another physicist who can control all of this. And that's obviously where this becomes extremely difficult. And in fact, at present, this is impossible for all practical purposes. But quantum mechanics, if applied to the universe, really does suggest to us this. Now, the final few slides where I want to stop with this kind of stuff before they lock me up and declare me completely crazy. But that's basically quantum mechanics for you. Is that frequently you hear people say, what does it feel to be in two universes, you know? And actually the answer is there's nothing to it, because each of the Bobs in our experiment is completely unaware of the other Bob. And even if through Alice he becomes aware, it's not that you feel anything that the other copy of you feels. You simply feel exactly as you feel in this classical universe. You feel there is only one copy of you and you are making your own observations. So it's very akin to the following, which I find also mind-blowing, and it's a picture of the universe that comes out of it, and I want to communicate it to you. Bell also wrote a lot about it. Basically, the answer could be that to be in another universe simply feels like to exist at another time. So according to this multi-entangled picture of reality that we have in quantum mechanics, other instances of time are nothing but other instances of quantum universes, really. So being in a different universe is really no different to waiting for a few minutes and just simply existing at another time. And no one feels particularly weird about that one. And what I've just outlined is something that's called Page and Wooter's picture of the universe. So actually the universe, this resonates very much with Einstein's relativity, which is why I'm telling you about it, because it seems to me that there is no need for any real fundamental conflict between the two. And to me, this is really the next big question. Can we properly test and unify quantum mechanics and general relativity? So here we have literally everything in the universe that will happen has already happened. And we have this big entangled quantum state that describes each of these different realities at each time, together with all of the different times in a hugely entangled wave function of the universe. And this to me is mind-blowing, because you have a fully static picture of the universe, much like in relativity, and yet things could be thought to evolve from one instant to the next instant. So this is the phrase evolution without evolution. And the supervisor of Page and Wooter's, another well-known physicist, John Wheeler, was the person who was suggesting these kind of views of reality. What I want to finish with, of course, is where we are technologically, because it is there's much work really left before we can test properly any of these things. And what I want to show you is at the moment what we are doing, if this to you looks like something that resembles coronavirus, I think you might be right. And in fact, this is something we would definitely like to do to coronavirus as a sort of revenge for what we are going through now. But it could be any organic molecule, it could be any living system. That would be exciting. So what I'm showing you is experiments that we are doing actually at Oxford. And you have a photon that's split here at the beam splitter, much like in the Schrödinger cat experiment. And then it goes towards one of these viruses. We have two viruses, one in each arm of this. And if the photon is absorbed by one of these viruses, it becomes excited. While if it's absorbed by the other virus becomes excited. And now you can see how this photon being absorbed will in fact transfer the superposition in which the photon exists into an entangled state between two viruses. So one of these viruses will be excited and the other one will not be excited, and at the same time, vice versa. And this would be the closest that we could get to, I think within next year or so, to a kind of Schrödinger's cat state. And I think there are many people who are going in this direction. And it's very exciting to really test whether quantum mechanics does apply to complex systems in chemistry as well as in biology. And finally, to close this notion maybe that some people are promoting, that when life gets engaged, these superpositions will collapse. Actually, what I'm advocating here is that nothing collapses. Quantum mechanics holds consistently at all levels, and we will one day really be able to create these kind of entangled states even with living systems. And behind the rest of the experiment here, the collection optics and everything is really there to implement a form of Bell's inequalities. So Bell's ideas about how would you verify that this state of two viruses or two bacteria is entangled, in fact, boils down to some kind of version of Bell's inequalities. So I'm going to conclude here, and it's a very brief conclusion because the statement here really is, it's an outline of reality that's fully based on quantum mechanics that applies to all objects and all scales. It's a very interesting picture because an observation is simply creation of entanglement between the observer and the observed. This distinction between the observer and the observed vanishes in this case, because when you entangle yourself to a photon, you yourself are entangled to the photon as much as the photon is entangled to you. There's absolutely no difference. It's a completely symmetric number. And in fact, it would suggest that whether you say that you're observing the photon or whether you say that the photon is observing you is simply a matter of semantics. It's basically both ways, if you like. This tells us that the beables, it's another term that Bell was very fond of. Beables are really quantum numbers. If you want to stick to locality, and I think there's absolutely no violation of locality in any of our experiments, that really means that the underlying reality is not made up of numbers. It's not a classical reality. It's a reality of matrices and operators and really weird entities, but somehow fully consistent and can account for everything that we observe. And the most exciting thing to conclude with is that it's a great time to be a physicist, because I think physics is now being taken from this microscopic domain into the macroscopic domain. I think it will elucidate many notions and concepts in subjects like chemistry and biology. But what excites me the most, of course, is that there could be another revolution in physics itself, because we still have this unfinished business of unifying quantum physics and general relativity. And with that, I would like to thank everyone for listening to me, and I would like to share my last slide with you. Thank you.
Thank you very much, Vlatko. Thank you very much for this engaging talk. Hello, everybody. I'm Mauro Paternostro. I'm a quantum physicist working here at Queen's, and I'm head of the School of Mathematics and Physics. And let me renew my gratitude to Vlatko for the fantastic talk. I have to say that the remote modality of delivery has only taken the away only the pleasure to see Vlatko in person, but certainly not the tantalizing nature of the questions that he has addressed. And also thank you to Chris Johnson, to Professor Chris Johnson, for his introduction to Vlatko. I'm in charge of, so to say, managing the question and answer session of this event, and I can already guarantee you, Vlatko, that we have quite a healthy number of questions, and I would like to invite everyone in the audience, in the virtual audience, to use the question and answer box that you find at the bottom of your screen. If you're using Zoom, we are all using Zoom, so please state your question, and I will make sure that within the time that we have left, your question is addressed to Vlatko. So Vlatko, if you're okay with that, I can start with the first question. If you're happy with, yep.
Yes, please.
So the question.
Please.
Thank you so much. So the question comes from Gleb Gribakin, who asks, when Alice communicates with Bob, doesn't she become entangled with the rest of the system?
Excellent point, actually, which is why one always feels dissatisfied when one speaks at this for a very brief amount of time, because there are many hidden complexities here. So I think the key issue here is that Alice asks a question, or, you know, as a physicist, you would say she performs a measurement which does not result in being entangled. And there are those kind of measurements that you can make. Of course, she could make a measurement which gets her entangled. And like I said, if she, for instance, asked Bob what outcome he saw, and if he said, I see a dead cat, then of course, Alice would automatically join that branch of reality. And the problem, there's no problem with this quantum mechanically, but the problem is that she would then not be able to undo all of the operations that are needed. And you would need yet another experimentalist who hasn't been entangled to actually do that for you. That's the tricky part of the experiment.
Thank you very much, Vlatko, for your answer. So I'll move to the next question, which comes from Matthew Belmonte, who asks, in your observing the observer thought experiment, what if Bob provides Alice probabilistic but not deterministic information on the state of the cat? For instance, suppose he answers that yes, he sees a live or dead cat, but his tone of voice suggests the probability of a live or dead state. How does the model of two superposed Bobs change?
It's another great question, because as you've now realized, in fact, it's not just whether Alice gets entangled to Bob or not. It's not simply a binary thing, but there are degrees to which Alice can become entangled to Bob. And in fact, quantum mechanics allows for this multitude of degrees. So it's possible that Alice performs a measurement that only gives a partial information about the outcome. And this would go exactly the way that you suggest. That Alice could ultimately just say, well, I can at best assign a probability to what I think Bob has observed. However, even this partial entanglement would of course affect Alice's ability to undo this experiment. You know, it would result to a reduction, if you like, of interference. But all of these possibilities exist in between.
Thank you again, Vlatko. So moving to the next one, this comes from Paco Vidal, who asks, how is observation or measurement defined? How does it differ from any other physical interaction? There is a second part to the question, but Paco elaborates on the question to some extent. So I would like to stop here and give Vlatko the chance to address his question at this stage.
Excellent. And again, this is precisely where my bias comes in. And I believe that this is the message from quantum mechanics, that measurement is no special interaction whatsoever. So this view that I'm advocating is precisely based on the fact that measurement is just another interaction, and it should be treated in exactly the same way as all other interactions. So whether it's certainly, you know, John Bell was great actually at making this very dramatic by saying, you know, how sophisticated. He also disliked the notion of observers and being different to observe and so on. And John Bell would say, you know, how sophisticated does the apparatus have to be to qualify as a measurement apparatus? You know, does it have to be a physicist? Is it enough to have a bachelor degree, or does it need to be a PhD in physics? You know, things like that. And I'm saying none of this is needed. Looking at two atoms getting entangled is no different to having a more complex system entangling to an atom. As far as entanglement is concerned, that's really all you need to qualify something as an observation. So this is, as it were, a minimalistic view. There are no measurements and they're not special at all in any way.
Thanks again, Vlatko. So Kira asks, oh, first of all, she states, this has been fantastic. I share the opinion.
Thank you.
Do you know if there is a theory of a fluid multiverse that accounts for quantum phenomena, dark energy, and singularity, and may suggest or hint towards a solution?
Another great question, actually, because I'm aware of a number of these models. In fact, I don't know how successful they are at explaining cosmological observations. And the problem there, of course, is that we have very few things that we observe at that macroscopic level. But it's very suggestive to go into fluid modeling, because ultimately, we should be describing everything in terms of quantum fields. So these fields are entities that exist at every point in space and every instant in time, much like a fluid, actually. They resemble fluids very strongly. And everything else we see around us, all the particles, all the interactions, should really be phrased in terms of how these fields, quantum fields, couple to one another. So I think a fluid-like model is definitely something that people are exploring, but what I'm not sure about is really whether they're giving us any predictions that are different to anything else and how well they account for all of these facts.
Thank you, Vlatko. So Jarek asks, is this multiple reality equivalent to Everett's many words interpretation?
Good point as well, because it's very hard from Everett's thesis to tell whether he would have agreed with this kind of experiment of observing the observer, but I would think that the answer is yes. So I think as soon as you admit that everything in the universe could be described quantum mechanically, I think you will invariably end up in one of the many worlds camps. I mean, there are many of them, I think, and lots of us even disagree with one another, but I think you are basically very strongly related to Everett's ideas.
So Steve asks, there are quite a lot of questions, Vlatko. So this was really thought-provoking to say the least. So Steve asks, if the wave function of the universe is basically static and evolution only appears to occur due to the pre-existing entanglement being present, how did the state of the universe get entangled in the first place? And this is Steve Campbell from University College in Dublin.
Yes, Steve, hi. Yes, it's a good point, actually. I think it's a picture that I don't like philosophically. And I think when John Bell wrote about it, he also wrote about it in a negative way, that he would say, if you push this to its extreme, it gives you this version of reality. So the question that you're asking would even not make sense within this, because the wave function would simply be out there. We would not have any explanation for how this wave function was set up. The best you can say is that it's one eigenstate of the Hamiltonian of the universe. Now, of course, as you know, it's unlikely that we will ever really either know this Hamiltonian or be able to describe the world in this way. So somehow this wave function of the universe would have to be taken as a primary entity. And I think the question of where does that come from would certainly lie beyond this theory.
So we continue with Paul Moorhead, who is a graduate in physics from Queen's in 1981. So Paul wonders, so there are physicists like Liz Molin who continue to search for alternate theories that would avoid some of the most unsettling aspects of quantum theory. Do you think this is a complete waste of time, or is it a useful challenge?
I'm going to be unkind and I'm going to go with a complete waste of time. But let me let me say why this is. I think it really comes from this choice that Bell gave us. So, you know, he said, really, you have to either give up this reality as classically intended, which is what I feel Lee Smolin would like to stick to, or you have to give up locality. Now, to a person like me, it seems much harder to give up locality, really, because this would introduce real magic in the universe, if you see what I mean, magic of the bad kind, you know, that I do something here and suddenly another electron on another galaxy changes. I mean, that surely cannot be like that. And I think if you say, I'm going to stick with locality, I'm not going to give that one up, then you certainly cannot have classical reality anymore. And I think actually the way that this is going to go is that whatever the beables happen to be after we quantize gravity can only be even more complex than the operators I was talking about now. So that's why I think his intuition to try to go back to real numbers as being the underlying reality is probably mistaken. I think if anything, it's going to become even more challenging in terms of imagining what it is. But I'm saying this because I think locality will remain.
Thanks, Vlatko. There was as far as I remember, there was a paper some 15 years ago in Nature saying a goodbye to locality, but it wasn't particularly well received, as far as I remember.
Yes, you are right, and I think again the terminology gets in the way, right? Because I think they meant some kind of Bell non-locality, which is precisely what Bell meant. It didn't mean violating relativity. Yes.
Absolutely. Okay, so just as a note to the audience, I think we have time for 2 or 3 more questions before leaving the stage to Professor McKenna from the Royal Irish Academy. So if that's okay with you, Vlatko, we can continue for a couple more questions?
Absolutely, absolutely.
Okay, so Mark Dagan, an engineer from Dublin, he asks, if all outcomes exist superimposed and time is static, what are the implications for free will?
Oh,
you have
another
a
great,
tough
audience, and you know, the honest answer is I don't know, really. I think it seems to me that this is a great question in the sense of something that will actually even be subject to our experiments. I'm already talking to various colleagues in neuroscience, because these experiments are getting more and more sophisticated at tracking how the brain processes information and observing how we make decisions. And I think there is a lot more mileage we will also get out of this kind of stuff. So I think if you really take this static universe, then I think free will, as we conventionally think about it, is out of the window. But I think what this could point to us is that maybe the way we define free will has to be different. So I think the problem we are having there is that it's not even clear what it means to have free will. You know, how would I set up an experiment that would really demonstrate to you that you have free will? In what I presented, obviously everything is done mechanically, and Bob is manipulated in the same way that another physical system would be manipulated, and so on. But it seems to me that the question of free will first requires a very clear set of ideas of what it is that we are trying to define. And secondly, I think it would be great to go in experimentally and probe this domain. Whether any of this has anything to do with quantum mechanics is hugely exciting, but none of us really know.
Last question, and I would like to ask this one on behalf of Fernando Garrido from the Dominican Republic. So just to give you an idea of how far-reaching you have. So Fernando asks, what would we expect if there were 2 such experiments being performed and depending on each other? So I think he's pointing towards the possible, say, interrelation between outcomes of different quantum experiments.
Yes, this is a great question as well, and I should say again, I don't want to really get too technical with these things at all. Is that there is a great deal of literature on this currently, and in fact, I think, I mean, I would say a lot of misunderstanding of these things. So something I didn't talk about at all, and I think you are alluding to this possibility, is that what if Bob makes a measurement, but Alice asks a question in a completely different direction, in a completely different basis? And quantum mechanics would say, yes, that's possible too. Some people think that this would be a contradiction in terms, but I simply think that this would be like a change of basis. What this would actually entail is that Bob would in fact become disentangled, if you like. In other words, he would lose recollection, he would lose memory of his original experiment, and he would simply continue to exist in this different superposed state. So again, if you apply the full quantum mechanics to everything in your laboratory, in your experiment, there isn't any contradiction. It's just that these consequences are simply mind-blowing. They are very unusual if you come to try to understand them classically speaking, but it's possible, and there is no contradiction, I think, with the formalism of quantum mechanics.
Vlatko, thank you so much. I would like to stop the question and answer session here. I can see already Professor Jerry McKenna camera on. And before leaving the stage to Jerry, I would like to thank everyone in the audience for their engagement with Vlatko. I mean, it's fantastic to see so many questions, and they keep on popping up. So thank you so much to everyone, and thank you, Vlatko, for the fantastic talk. I can reassure you that the connection was playing well, and it was visible and hearable in a perfect way. So I would like to leave the stage to Jerry, and Vlatko, we will thank you appropriately the first time we will meet, which I hope will be soon. Thank you so much.
Thank you.
Thank you.
Thanks a lot.
Well, thank you, Mauro, and I'm delighted to say a few words, very few, on behalf of the Royal Irish Academy. As we heard on the 4th of November 1964, John Bell from Tates Avenue here in Belfast changed the world of science by laying the foundation stone for quantum computing with his quantum theory. And since November 2014, the Royal Irish Academy has worked with Queen's University in Belfast to mark the achievements of Northern Ireland's son by celebrating the John Bell Day. Our aim is to make John Bell a role model for the young people of Northern Ireland, to inspire them to see education and science as a route by which they can fulfill their greatest ambitions, like Bell did. The Royal Irish Academy is Ireland's all-island academy, recognizing excellence in the sciences, humanities, and social sciences. And about a quarter of our members are based in Northern Ireland. We welcome the opportunity to work with our colleagues in Queen's University in organizing these events for John Bell Day. We would like to thank in particular Professor Mauro Paternostro, the head of the School of Maths and Physics, who has been the organizer, the academic organizer of these events and has played a huge role in their success. Also Professor Chris Johnson, Pro-Vice Chancellor for the Faculty of Engineering and Physical Sciences, whom we heard earlier, and behind the scenes, Dolores Fisher and Robbie McGreer from the Public Engagement Office. Finally, heartfelt thanks to Professor Vlatko Vedral for giving so freely of his time and expertise today, both in the earlier student unplugged session and for his wonderful John Bell Day lecture. We've all been greatly inspired by the lecture, which will influence our thinking, moments of discomfort and reflection for a long time to come. And this brings us to the end of our event today. So on behalf of the Royal Irish Academy and Queen's University, I would like to thank all of you for your attendance, your questions, and your participation. Thank you.